So the normative economics theory suggests that we integrate anticipated outcomes and probabilities of the outcomes via a relatively cold rational cognitive process. And actually emotions are just byproducts of this cognitive process. So implicitly, normative economics theory suggests that emotions play no functional role in the decision-making process. But many modern theories, economic theories of decision-making, suggest that emotions play a critical role in the decision-making process. For example, semantic marker hypothesis or risk as a feeling hypothesis. They both suggest that our emotions critically contribute to the decision-making process. So we know now that emotions can be triggered by the processes underlying calculations of the anticipated outcomes. We also know that estimations of probabilities can directly trigger emotions. So actually, neuroeconomics studies show that both processes, the calculation of the anticipated outcomes and the estimation of the probabilities of the outcomes, take place in their fundamentally emotional brain areas. So it looks like emotions play a critical role in the decision-making, and they interact with cognitive mechanisms of decision-making during the process of decision-making. So today we will focus on the interaction of the cognition and emotions during the decision-making process. So of course we know, for example, that we can self-regulate emotions. Let's make a look now to a very elegant study conducted by Maurizio Delgado. So imagine that you have to pay attention on the screen and you will see different cues. So the color of the cue can indicate a monetary reward. So blue square can indicate a monetary reward at the end of the trial. Imagine that you can be in two different conditions. In condition A, you have to attend the reward-related aspects of the cue. So you have to focus on this cue and think about the aspects predicting the monetary rewards. In the condition B, you have to regulate your emotions. You have to think about some aspects of the cue, relaxing aspects of the cue that, for example, are linked to nature. You can think about ocean and self-regulate your emotions. So let's make a look into the details of this experiment. So here you see two different cues, and one cue predicted monetary outcome, another one predicted no monetary outcome. And subjects attended two different conditions. In one condition, they attended the aspects of the cue related to the prediction of the monetary reward. In their self-control condition, they actually tried to focus on the relaxing aspects of the cue. For example, on something in nature related to the color of the cue. For example, they thought about the ocean. So let's make a look first to the arousal of the subjects in different conditions. On the right side of the slide, you see the results of the skin conductance responses recordings. So you see that when subjects attended the reward-related features of the cue, predicting the monetary outcomes, they were particularly aroused by the cues predicting monetary rewards, as compared to the cues predicting no monetary rewards. So CS plus here indicates the cues predicting rewards, and CS minus indicates the cues predicting no rewards. So obviously subjects here were much more aroused during the anticipation of the monetary rewards. But in the condition when subjects self-regulated emotions, we see no difference between cues predicting rewards and predicting no rewards. So subjects successfully self-regulated emotions in this study. But let's make a look inside of the brains of our subjects. So first of all, we will see that the ventral striatum nucleus accumbens was activated when subjects anticipated monetary rewards compared to the trials when subjects anticipated no monetary rewards. But please make a look to the right side of this slide. You will see that this differential activity is particularly strong in the condition when subjects focused on the reward-related aspects of the cues. And this differential activity was attenuated in the self-regulation condition. So particularly in the first condition, nucleus accumbens was activated when subjects expected monetary rewards. And actually when subjects self-regulated, this activity in the ventral striatum was seriously reduced. But which brain region is activated during the self-regulation of the emotions? This study shows that dorsolateral prefrontal cortex is active when people regulated their emotions. So as you see at the lower part of this slide, the dorsolateral prefrontal cortex was particularly active when subjects regulated own emotions. So it looks like when we self-regulate emotions, we can modulate the activity in the ventral striatum in the key region related to the valuation process. And it looks like that this self-regulation process is associated with the dorsolateral prefrontal cortex. So we can summarize this study in two important points: that both physiological and neural correlates of the reward expectations are modulated during the emotion regulation. And self-regulation perhaps is associated with the dorsolateral prefrontal cortex. So during this lecture, we will focus on the activity of the dorsolateral prefrontal cortex. Many neuroeconomic studies show that this is a key region for the self-regulation of our emotions. So it can modulate the activity in the ventral striatum and in the orbitofrontal cortex. So today we will focus on the interaction of the cognitive process and of the emotional process during the decision making. The idea that different processes can contribute to the decision making process is not new for neuroscience. So here I show you the scheme suggested by the prominent neuroscientist Edmund Rawls, showing and illustrating multiple routes of action production in our brains. So we see here that some actions can be produced by relatively limited number of neurons in our spinal cord or in our brainstem. These are reflexes. We do not need many neurons to produce reflexes. But our decisions and more complex actions normally engage more complex neuronal networks. So for example, our decisions can engage the activity of the striatum. More complex decisions, more complex actions need the activity of the orbitofrontal cortex and amygdala, particularly when we have to integrate a certain context into the decision-making process, and we have to base our decisions on values learned previously during the previous trials. But some of our very complex actions and decisions can engage language cortex. So Edmund Rawls suggested that language cortex can lead to explicit decisions and explicit behavioral responses. But currently, I think the majority of neuroeconomists think that dorsolateral prefrontal cortex plays a critical, vital role into the cognitive control of the decision-making process. So the idea that multiple routes can create decisions inside of our brain is not new for neuroscience. So perhaps some decisions are underlined by the activity of the striatum, some decisions are underlined by the activity also of orbitofrontal cortex, amygdala, some engage even dorsolateral prefrontal cortex. Sometimes perhaps these different routes can even conflict with each other. But in economics, this idea is also not new. So let's make a short break, and I will ask you a very simple mathematical question. So a bet and a ball costs $1.10 in total. The bet costs $1 more than the ball. How much does the ball cost? Perhaps some of you gave the correct answer, 5 cents. But some of you made mistake. So basically many people report in this situation that they have an internal motivation to say 10 cents. And don't be disappointed if you made this mistake. Half of the Princeton students made the same mistake in the original study. So here we can make a fast but wrong decision based on certain heuristics. We can give the wrong answer, 10 cents, very quickly. Actually, quite often this wrong answer can be okay. It is not so far away from the correct answer. But in some situations, this mistake can be, of course, vital. So this idea was nicely summarized in the hypothesis suggested by Daniel Kahneman, that sometimes our decisions are based on system 1, intuition-based system, and sometimes our decisions are based on more reasoning-based system, system 2. So system 1 is more fast, automatic, often emotional system. And system 2 is more slow, controlled, cognitive system underlying certain decision-making. So interestingly, system 1 is very fast, and it can operate and it can integrate really large amounts of information because it processes the information in a parallel fashion. So system 2 is slower and it processes the information in a serial fashion, one by one. So it has a limited capacity. So Daniel Kahneman was not the first psychologist and economist who suggested that we have different systems underlying decision making. So here in this table, you see a summary of very different theories suggesting basically the existence of system 1 and system 2. So some of the theories suggest that system 1 is impulsive, system 2 is reflective. Some suggest that system 1 is heuristic based and system 2 is analytic. Some suggest that system 1 is implicit, system 2 is explicit, but basically all of them suggest that system 1 is faster, more emotional, and system 2 is slower but more cognitive. So we can summarize the idea behind the theory of two systems, that system 1 is typically fast, automatic, implicit, and often emotional, and system 2 is slower, it looks like it is consciously monitored, and perhaps system 2 is able to monitor and supervise the activity of system 1. Does it mean that system 2 is superior to system 1? No. You remember that system 1 has much larger processing capacity. It can process large amounts of information in parallel. System 2 actually has a limited capacity, so in some situations, system 1 is superior to system 2. And this is nicely illustrated by very interesting studies conducted by Dexterhouse in Holland. So Dutch scientists created a very interesting experiment. So in this experiment, subjects were asked to evaluate different hypothetical cars. So in the simple version of the task, they had to estimate 4 attributes per car. In the more complex version of the task, they had to estimate 12 attributes per car. So each attribute contained either positive or negative information about the car. So subjects attended 2 different conditions. In conscious thought condition, participants had 4 minutes to think about the best car out of 4 hypothetical cars. In unconscious thought condition, participants were distracted from the active thinking process by 4 minutes of solving anagrams. So they didn't have time to think really about the optimal decision. So the results of this study looks quite counterintuitive. So you see that in the complex task, when subjects integrated 12 features, 12 attributes per car, subjects performed tasks better if they didn't have time to think. And this pattern is reversed for the simplest version of the task. So interestingly, when people do not have time to think about the complex information, they can come up with a better decision than in the situation when they do intensively think about the task. So actually, Dutch scientists replicated this finding in the more real-life context. So they interviewed shoppers near 2 different stores. So they asked various questions, customers near IKEA that sells more complex products, or near Bijenhof, the store that sells more simple products. So they asked various questions. What did you buy? How expensive was the product? And how much did you think about the product? And finally, in a few weeks' time, by phone, they asked customers how satisfied they were with their purchases. And once again, we see here the same trend. When shoppers made more complex decisions in IKEA, they were more satisfied if they didn't think a lot about their decisions. And this pattern was reversed for the Bijenhof, where subjects make simpler decisions. So overall, System 1 can be superior to System 2 in certain contexts, particularly when we deal with very complex information.